energy and conservation of energy. Does anybody have any questions about the test tomorrow? I mean, logistically, I guess I should say that just show up at the normal time. Actually, if you want to, can I say if you want to show up a few minutes early, you could do that. I'll see if I can get out of advisory. Well, no, I don't know if that'll. Yeah, I'll try to get out of advisory and see if I can get to the classroom maybe 5 or 10 minutes early and just get on the Google Meet then and make the test available so that if you're at home and you want a little more time, you can do that. On the other hand, if you're at home, it doesn't really matter if you spill into fourth block. So if I don't get it together and I'm not early, then you'll still have some extra time. But at any rate, I'll open up the Google Meet and then I will send everybody the tests in Google Classroom and the directions will be there. You can either print it out or just do it on another sheet of paper. And the math teachers, if you're taking a math class, you're probably familiar with this. They've started having everybody take pictures of their solutions and put them in a Google Doc and then turn in the Google Doc, and that works well because I can take that Google Doc and just download it as a Word document and then I can mark it up and send it back to you as a PDF. So, but I'll have instructions about that. One way or another, you just have to get your solutions to me. It could be, sometimes people send me a bunch of pictures in email, which that can work too, but try to follow the directions. But back to my first question. Does anybody have any questions about the test in general? No, hopefully you're all there.
Can we submit it as a PDF?
Yeah, you can submit it as PDF. Yeah, especially if you have a scanner app, you can do that. It works nice. The scanner apps will clean things up, make it easy for me to see. That's fine. And you can just do what you've done before if you've done my test before. The Google Doc saves me maybe a little step or two, but it's not a big deal. Any other questions? Does anybody have any questions about any of the content that's on the test? All right. Well, you can always interrupt with more questions about that. So, the warm-up. These are graphs of net force versus position. So, this would be the force applied to an object and when it's in different positions. A, B, and C kind of make sense. D is a little weird. I'm not going to give away what's going on with D, at least in my mind. So A just shows that when something is at a position of 0 meters, you can picture it on a number line. The object's sitting right here at 0 meters. There's a net force of 5 newtons acting on it. And then when the object's at 1 meter, still 5 newtons acting on it. And when it gets to the 5 meter mark, still 5 newtons acting on it. All the way. So constant 5 newton force over this entire 10 meters. And your job here is to calculate the amount of work represented by each graph. So you know what? I'm gonna pick. Oh shoot! I don't think I've updated my little popsicle stick thing here. I have all my classes are from the other term, so I'm just going to randomly pick a circle here. And this is kind of nice. I can't see your names. So Carlota, I've chosen you. So for A, can you tell me the amount of work done that's represented in graph A here? And if you don't have an idea, just say give me a hint, and I'll give you a hint. Carlota, are you there? There you are. Do you want a hint? Uh-oh. Can't hear. Are you talking? I kind of hear some, but that's it. Let me pick somebody else. All right. Who's this? Julia. Chosen you. So Julia, how much work is done there? Julia? I can't hear you. Are you talking? Carlota's saying, can you hear me? No, I can't. I could hear Ollie earlier. Ollie, will you say something? I want to see if I can still hear you.
Can you hear me?
Yeah, I can hear you fine. I couldn't hear Carlota. I don't know if Julia, were you talking? You can put it in the chat. Oh well. So Ollie, let me just ask you then, because I know I can hear you. Sorry about that. Um, do you know how much work is done in A?
Can I get a hint?
Yeah, work is force times distance. So if you know how much force is applied and you know the distance over which it's applied, you just multiply them together.
Cool, so it'd be 50.
50 joules in this case, 50 joules of work.
Joules.
And this is just a straight up constant force problem. So 50 or 5 newtons applied over the entire 10 meters. Now, can anybody tell me how much work is done in B? I won't put anybody on the spot, but how much work would be done there? Any ideas? Then this one's different because the force changes. So at the beginning there's really not any force, but then the force is stronger and stronger and stronger, and by the time the object's at a 5 meter position, the force is 5 newtons, and then force diminishes again.
25 joules.
25 joules. Yeah, who was that?
Jackson.
Jackson. All right. So how'd you do it, Jackson?
Area of a triangle, base times height over 2.
Yeah.
5 times 10 over 2.
Right. So sort of he's jumping, making sort of a leap of understanding that the simplest way to explain going from A to B is just to say in B you can use the average net force and multiply that by the distance, and that'll give you the right answer. So since the net force goes from 0 up to 5, in this beginning here the average is really about 2.5, and then when it drops from 5 down to 10 or down to 0 again, the average is 2.5. So we could just assume an average net force of 2.5 times the entire distance of 10. 2.5 times 10, 25. But another way to do that is to find the area under the curve. So we've done some areas under the curve before. If you measure or calculate the area under this 5 meter mark, so we go over 5, we go over 10, down 5, this area would be 50. Here we've got a couple of triangles, or I guess you could see it as one triangle, that if you calculate that area it's going to be 25. So think of it as average net force multiplied by distance, or you could think of it as the area under the force curve, and you'll get the same answer. All right, C. Think about this one. I want to know how much work is done there, and I need to do it in my head first before other people, so I can tell you if your answer's right. All right, does anybody want to answer C? How much work is done in this one?
Is it 37.5? I may have messed up the mental math there.
I think so let's check. This first part, the area under the curve would be
25 divided by 2?
yeah, 25, so that'd be 12. And then the
Is that
second,
12.5?
yeah, that'd be 12.5. And then the second part is 5 times 10, which is, or 5 times negative 10, which would be,
15.
yeah, and then divide that by 2, you get negative 25. So the area, yeah, so you just did the 50 minus this 12.5. But this
No,
would,
I added the two together.
oh, I got it. Yeah, so if you add the two together, you get 37.5. And if you consider this to be a negative, then you get negative 12.5.
Sorry.
Well, no, that's perfectly okay, and that sort of raises this interesting issue of I want to see I'm curious to see if we can interpret this graph in a way that makes your answer right. And the answer I was thinking was negative 12.5 because we're doing positive 12.5 joules of work here and negative 25 joules of work here. So I was adding them up to get.
Direction and make that.
What's that?
If it changed direction,
Yeah.
acceleration would change. I guess I don't know that it really counts. But.
Right. Yeah. So let's not even mess with D for a second. D is just bizarre. But I added it in there because I think it's interesting and maybe it can help us learn something. So. This is related to part 2, and it's related to a question somebody asked me yesterday about the idea of negative work. So let's talk about 2, and then we'll come back to C in a minute and see if there's a way. I'm just wondering if both of our answers could be right. So if we look at situation A, where there's a net force of 5 newtons applied the entire time and 50 joules of work done, can we say what the change in kinetic energy is for graph A? Like if this is an object, if this is a box that's being pushed, do we know what's happening to its kinetic energy? And I'm going to switch to my camera for just a second. And sort of the quick answer that I'm hoping you're thinking of is yes. So the net amount of work done on something equals the change in kinetic energy. So if you have a box and you're doing some work on the box, say pushing the box to the right, you're applying a force to it, and you do that for some distance, d, then you're going to do some work and you're going to change the box's kinetic energy. But does that mean I'm giving it more kinetic energy or less kinetic energy? What do you think? Or can you not tell? Like in this particular case, this is a 5 Newton force, and here it's applied at different distances. I could actually make an argument that this could be interpreted as decreasing the kinetic energy, or it could be increasing the kinetic energy. So I guess the question is, how could we interpret this as being a decrease in kinetic energy? Can anybody see what I'm thinking of here? We've got a positive amount of work done based on what I've told you, but I'm saying the kinetic energy is decreasing by 50 instead of increasing by 50. How could that be? Alternatively, could be that the kinetic energy is increasing by 50. So, and it boils down, since nobody's answering my question, it boils down to which way this thing is moving in the first place. So this block, if it was moving, if it had an initial velocity to the left, and we're pushing it to the right, is that going to increase its kinetic energy or decrease its kinetic energy? The answer is we're going to slow it down. If it's moving left and you have a net force to the right, you're going to have an acceleration rightward, and that's going to slow things down. I guess I should write net force, because that's what we're talking about here. So the acceleration is actually to the right also. But alternatively, if you had the block and its initial velocity was this way, and the net force is to the right, and therefore the acceleration's to the right, then we're going to be speeding it up. Remember, kinetic energy is 1/2 mv squared. So if we don't change the mass, but we do change the velocity, we're going to change the kinetic energy. Here, we're decreasing the velocity. Well, wait a second. I mean, what's really important here is the velocity squared. So for kinetic energy, it doesn't matter if you're going left or you're going right first. I mean, this, we could say this is negative, we could say this is positive, but when we square both of these, we're going to get the same kinetic energy. But by pushing this to the right, that's going to decrease this value, the absolute value of it. And by pushing this to the right, that's going to increase the absolute value of this. So going back to the graph, is there anything about this graph, graph A, that tells us the direction this is moving? Raise your hand if you think there's anything indicating the direction it's moving. Okay, good. No hands. I'll stop before somebody raises a hand. No, there's no time here, so we don't know whether it's at the 10-meter mark first or if it's at the 0-meter mark first. This is just position. So it could be this is where it is first, and then it's here, and then it's here. So this thing could be moving to the left, and if it's moving to the left, then this this positive work is going to be, this positive force is going to be decreasing the kinetic energy by 50. If it's moving to the right, then the force to the right is going to be increasing it by 50. And I was trying to think through all these formulas and see if there's just a foolproof way to plug and chug, and I can't think of one. I think you just really have to, you're going to have to be careful and think about directions and think deeper than just the formulas on this. All right, so B. If we think about B, we calculated the area under this curve as being 25 newtons, but, 25 joules. So the change in kinetic energy is going to be 25, but again, we don't know if the thing was moving to the right in the beginning or moving to the left. So it could be, if it was going leftward and being pushed rightward, it's going to lose 25 joules of kinetic energy. Now this one, let's see, moving to the right or moving to the left? Now, I'm going to imagine that this was moving leftward. So what's happening here in the beginning is there's a whole bunch of leftward force multiplied by this distance. So it would be gaining kinetic energy, and then it would be losing kinetic energy, but not as much. So I would still say that the change in kinetic energy, if this is moving from right to left, would still be this area minus that area. And if it's going to the right, if it's moving right the whole time, then it's going to be like accelerated by this force, and it's going to gain a certain amount of kinetic energy, but then it's going to lose even more. Now, one thing to think about is maybe it accelerates to the right and then it starts to lose kinetic energy and it goes back to the left. But I don't know if that can really happen, because if we had an object that went to the right and then went to the left, we would have something like graph D over here. And that's not what's shown here. So Ada, when I was trying to think about maybe there's some complicated scenario where something could move one way and then another way, and the answer that you gave would actually be right, but I don't think so. I think that if we think about what's happening in D, you can have the same different net forces in the same positions if you have an object that, let's say, moves to the right and then gets pushed back to the left. So this would be maybe it's force when it's going to the right, and then this is the force when it's going. Actually, no, that wouldn't work. This would have to be the force when it's going to the right, and this is the force going to its left, to the left. Let me show you what I mean by this. So if you have this, first, it's probably easier to imagine something on a spring that's just bobbing up and down. So it goes down and then it comes back up. And as it's going down, it's getting slower and slower and slower, and then it starts to accelerate back up. So if we imagine something like that here, where somebody gives it a push, an initial velocity, and it starts to stretch out a spring, and it stretches and stretches and stretches until it gets to here, and then it stops, and then it turns around. What we would have is, throughout this whole thing, the spring would be applying a negative net force. I don't know. No, that doesn't really, that spring scenario doesn't work. So, could something move from 0 to 5 and have a positive force? I think my drawing was impossible. I'm not going to sit here and ponder it for a little bit, but maybe if you want to think about it later, I'm going to think about it, and I'll get back to you on this. I was thinking it was possible that something, as it was moving from here to here, might have a rightward force the whole time, and then as it goes back, it might have a leftward force. Okay, I've got it. That could happen. No, I don't think it could. All right. I think D is impossible, but I'm going to think about it a little bit more. All right, now what I would like you to do, everybody, sketch a graph of net force versus position for an elevator traveling from the first floor to the second floor. Assume that the elevator starts and ends at rest. Calculate the total work for the motion that you graphed. So draw a graph of net force versus position. And this is the second floor. Here's the first floor. So what this looks like is the initial velocity is 0, and then the elevator moves up. It stops right here, and the final velocity is 0. And what I want you to do is try to sketch a graph of force versus position. You can make this height if you want to. So this could represent first floor, or I don't know. I'm going to say I'm going to do 0. This is the height in floor. This is the first floor. This is when it gets to the second floor. So really, it's this area in here that I'm curious about. So you try that. I'm going to switch back to, actually, maybe I'll just wait. I'll just leave it like this. Think about that for a minute. And I guess this would be the upward direction, and this would be downward. Don't worry about specific numbers. We don't know the mass of this. We don't know the speed of it or the acceleration. Ooh, but we do know this should be net force. All right. Does anybody want to tell me what this would look like? Does anybody have some confidence about how this graph would look? Sorry about my grease on my hand. I was snow blowing and I broke a shear pin and I got a bunch of grease on my hand. Haven't gotten it off yet. Anyone? So here's where the elevator is on the first floor. Here it is on the second floor. And it's got zero velocity. So as it starts to travel up, what sort of force does it need? A positive force or a negative force when it's getting going, when it's starting to move to the second floor?
Positive.
Positive, yeah. So don't know exactly how this would look, but the force should be positive in the beginning. Now I don't know if you saw me draw this over on the side, if you were watching that, but we've done acceleration versus time graphs before. I feel like this was actually a question on a test. So if this is time and this is acceleration, the initial acceleration is going to be positive, and then as this elevator goes up, does it accelerate the whole time, or does it eventually come to like a maximum speed and stay there for a while? Depends on the elevator. I mean, it could if it's a long trip, usually an elevator speeds up, and then maintains kind of a constant speed, and then slows down and stops. But who knows in this? So there's upward acceleration in the beginning, and then at some point the elevator stops accelerating. And then in order to come to a stop, it's got to have negative acceleration to slow down, and then it gets back there. So acceleration, since F equals ma, acceleration is proportional to force. So that's the same, this is going to look the same way. There's going to be a strong force that's going to get this moving up in the beginning as it's accelerating. And I don't know if it accelerates really fast and then maintains kind of a constant speed. I mean, I could make it look like that. But whatever kinetic energy this gains in the beginning, it has to lose. So this area under the curve right here is equal to the force times distance, the work done on the elevator as it begins to accelerate. And in order to slow it down, we've got to take that kinetic energy away by having an equivalent negative area. So it should look something like that. And it's important to note that even though there's a lot of energy going into this elevator to get it from here to here, it's not kinetic energy. Work equals a change in kinetic energy. The new concept that I'm going to talk about today is the kind of energy that has been put into the elevator. So compared to when it was on the first floor, it has more energy now on the second floor, but that's not kinetic energy. Does anybody know the name for that energy? Potential energy. And potential energy is the thing we're about to get into. Let's see. So I guess I've answered number 4. Number 3, it takes energy to lift an elevator. Where does the energy go? It goes into potential energy. I better quit looking at this. I want to go back to D and think about that situation more, but I'm not going to. All right, 10:30. We don't have much time at all, but we'll do a little bit, and then probably not get to the roller coaster thing until after break. But that might be a good way to get back into things after break. So I'm going to the notes. Give you a moment to get these out if you want to get them out, although I know some of you don't have them yet. Potential energy. If you've learned about kinetic energy, you probably learned about potential energy. And it's stored energy It can have many forms. You can have gravitational potential energy. That's the one that we're going to be dealing with mostly here until we get to springs. Then we'll use springs. Spring energy and chemical energy. We're not going to do much with chemical energy. Nuclear energy, anything like that. So PE gravitational. This is work done against gravity resulting in a change in gravitational potential energy. I was thinking about this earlier, and I can tell you in a little while why I was thinking about it, but you can think about potential energy as being sort of like a spring. So you've got a person and the earth. If you take this person and you pull the person away from the earth to here, you're storing energy in that person. You pull them even farther away, and you're storing more energy in that person. If you let go of the person out here, that energy that you've stored is going to turn back into kinetic energy, and the person's going to fall to the earth. So that's kind of like, it's kind of as if there was a spring connecting the person and the earth, and as you stretch the spring farther, you're storing more and more energy there. The difference between this and this is that the farther you stretch a spring, the tighter that spring becomes. But when you lift a person farther and farther and farther from Earth, the weaker the gravitational force is. So they're a little bit different, but it's the same kind of thing. When we do problems relating to potential energy and energy conservation, it helps to remember that the person and the earth are kind of part of the same system in all these problems. And again, I'll come back to that. So for objects that are being lifted, the minimal possible work done in the process of lifting an object to a certain height equals the force of gravity multiplied by that height. So in the case of the elevator here, if it has a certain mass, and therefore the weight equals mass times gravity. If you want to lift that elevator this height g, then you're going to have to do some work on it, which is going to equal to the force, which is mg, that's the force you have to apply to it, times the distance, which is the height. And when you do that work on the elevator, you're going to give it energy. Now you're not going to give it kinetic energy because it's not gaining speed in this case. You're just putting energy into the you're giving it potential energy. Let's see. So delta PE, change in potential energy, equals mgh. So if you climb down a mountain, you can lose potential energy if your h is negative. And if you climb up, you can gain potential energy. An object which is already situated at some height can be thought of having stored gravitational potential energy. Now, one of the things about h in this formula, when you're calculating it, is like the question of where is h equal to 0. And that can be flexible. You can set any 0 height you want, and then you can say, 5 meters higher equals an h of 5. A lot of times, just the basic idea of where height would be 0 would be the surface of the earth. But if you dig a hole, if this is the earth, and you dig a hole in it, and you've got a person next to it, you could still release some potential energy out of that person by dropping them in the hole. So if you wanted to calculate the amount of potential energy, this would be the height that you would use. So where h begins is just flexible. All right. Energy conservation. Unless there's friction or an external input of energy, the total amount of mechanical energy in a closed system remains constant. And in the beginning, all we're going to be doing is saying that the kinetic energy plus the potential energy that you start with equals the kinetic energy plus the potential energy that you end with. And a classic example of this is maybe a skateboarder and a half pipe, a frictionless half pipe. As the person goes down and then comes back up, if there were no friction, this would just happen, this would go on forever and ever. And in the beginning, this person would have a lot of potential energy, and at the bottom, there'd be no potential energy, they'd have all kinetic energy, and then as they go up, they would have all potential energy again. And somewhere at this halfway point, this much potential energy is lost, but it's turned into an equivalent amount of kinetic energy. And then the kinetic energy keeps building while the potential energy keeps getting lost, but the total is the same. So the total initial energy equals the total final energy, and this applies to mechanical energy. We're really not talking about chemical energy or anything yet. Heat is not included in this. So, yeah, I'm not going to say more about that. All right, number 7. This is an application of these things. 3 kilogram watermelon is dropped from a height of 100 meters. What is its potential energy at its release point at 100 meters? So that's just the potential energy formula, gravitational potential energy. I'm not going to write PE gravitational every time. Equals mgh. And the mass is 3 kilograms. G is 9.8. H is 100 meters. And I'm just going to cheat and look at my answer to this from the past. So that's 2,940 joules. That's how much potential energy the watermelon had at the release point. Now, what is the watermelon's potential energy when it's fallen to an altitude of 25 meters? So it's same thing. It's still the potential energy formula. It's going to be mgh. I'm not going to write that again. I'm just going to write the mass times 9.8 times 25 meters, and that gives me 735 joules. So this is how much potential energy it had in the beginning. This is how much potential energy it has after it's fallen 75 meters. So how much kinetic energy does it have? The kinetic energy must equal the amount of potential energy it lost. And I'm not going to just write that. I'm going to write out this formula here. So if I take this formula and I substitute things in, I don't know if it says, it doesn't say it was dropped from rest, but when you drop something, it doesn't have any velocity. So the initial kinetic energy is 0 joules. That's the kinetic energy when it's first dropped. And its initial potential energy is 2940. So this represents the total energy that it had in the beginning. And that should equal the sum of those two energies at the end. So kinetic energy final plus the potential energy final. So I've got 2940 equals KE final plus 735. So I just subtract 735 from both sides, and we get the final kinetic energy, which is 2205. And finally, number 10, what's the watermelon's velocity when its altitude is 25 meters? So we can use the kinetic energy formula for that. Kinetic energy equals 1/2 mv squared. So 2,205 joules equals 1/2 times the mass of the watermelon times its velocity squared. And to solve this, I'd do 2205 times 2 divided by 3 and then take the square root. That ends up being 38.3 meters per second. So we could have done all of this with with stuff we have done before, you know, something's falling, it falls 75 meters, we could have figured out what the velocity was just using kinematics, but this is another way to do it. And arguably maybe a simpler way to solve some of these things without kinematics formulas. All right, let's go do a little bit more. Actually, I think I'm gonna call it a day here. So we're not getting to this roller coaster problem. We're not getting to the energy added to or stolen from a system. But after break, this is going to be the first thing we're going to do. Try to figure out, fill in this table, the kinetic energies, the velocities, the potential energies, the total energies at a bunch of different places in this this event. And hopefully that'll be a good way to rehash things that you've forgotten over a couple weeks. That's it. If anybody wants to hang out, you can hang out. If you want to go, you can go. I'm gonna, as soon as I get a chance. You're welcome.
Thank you.
You're welcome. You're welcome. You're welcome.